A very good morning and welcome to this course on the foundations of continuum mechanics. Today we will be going through the third week's tutorial. So let's get started. The topics we'll be covering in this tutorial are on matrices and determinants, on tensor transformations, and on isotropy and invariance. So let us get started with the problems. So the first problem is written here. And you can also have a look at these problems in the tutorial sheet that is shared on the NPTEL portal. So the problem says that we have to show that the determinant of a skew symmetric matrix is 0. So let us show that. So it is a skew symmetric matrix. So we can write the property of skew symmetric matrix as, let us say we are dealing with the matrix A, then Aij is equal to minus of Aj. That's the property of a skew symmetric matrix. Next, we have to find the determinant of this matrix A. So let us write the expression for the determinant in the initial notation. So this is the expression for determinant epsilon ijk a1i a2j times a3k. Now what we'll do is, in this expression, we will substitute the skew symmetry property of A. So that becomes an epsilon ijk, and then an a1i becomes a minus ai1, a2j becomes a minus aj2, and a3k becomes a minus ak3. So we have three minuses, so that becomes a minus overall. Epsilon ijk, ai1, aj2, and ak3. And we also know, and you can check from the lectures earlier this week, that these two are two forms of writing the determinant of A. So we can either write it the row way or the column way. So it can be A1i, A2j, A3k, that is the three rows, or we can have AI1, AJ2, and AK3, that are the three columns. So this is minus times determinant of A. So what we have got is that determinant of A is the negative of determinant of A, which basically means that the determinant of A is 0. And this is exactly what we had to show, that it is equal to 0. So we have shown that, so that completes the solution. In fact, this can be used as a property as well while trying to solve other problems. So you can take it as a property that the determinant of a skew symmetric matrix is 0. So let us move on to the next problem. So the problem 2 is that we have to show that determinant of A is epsilon ijk, a1i, a2j, a3k. And this is something we have been using, and I mentioned earlier as well that we will show it as a problem in the tutorial. So here it is, and it's a hint provided to us that we can use the idea of scalar triple product to show this. So let's solve this. So first we must figure out how we will proceed with this. On the left hand side is determinant of A. Now what exactly is the determinant of A? Because we cannot use the initial notation. That is what we have to show in this problem. So determinant of A is written as this mod, and we know how to expand this. So this is something we will agree as a taken and proceed with this. So we'll show that this mod, which we know how it expands, is equal to the initial expression epsilon ijk, a1i, a2j, a3k. Of course, we can expand the initial expression and we'll get this, but we'll want to use a more elegant way to show it. And the right hand side, of course, is the initial notation involving epsilon ijk. And it is provided as a hint that we have to use the idea of scalar triple product. So let's do that. So the scalar triple product of three vectors u, v and w is given as or written as the box uvw, which is, there are many ways to write it. So we are using this form u cross v dot w. You can also write it as v cross w dot u or w cross u dot v, or you can also write u dot v cross w and so on. So we have already discussed that. So we can use any form that we like as long as the order is uvw, so that the sign does not change. So first we'll approach this to the left hand side way, that is we'll write the scalar triple product of uvw, that is the box product uvw, as the mod in the determinant. So let's see what u cross w is in the mod form. So the cross product of two vectors u and v is written this way, which if we expand becomes this in the form of the three components. Now we will take a dot with w. Now when you have a vector like this and you take a dot of this with a vector, what you end up getting is that this E1 gets replaced with W1, then you have this minus you have a W2 plus you have a W3, because W1 E1 gets dotted with this mod times E1, so that becomes this mod times W1. And seeing the same analogy, I can actually write this as W1, W2, W3 instead of E1, E2, E3 in the cross product, and then you have a U1, U2, U3 and V1, V2, V3. I can also perform two row swaps and the sign remains the same of the determinant. So this becomes U1, U2, U3, V1, V2, V3 and a W1, W2, W3. So this is the form that we will be using on the left hand side of this expression. So I'll summarize this. So the scalar triple product of u, v and w is written as, so let us call this A. Now we had also shown in the previous week's lectures that the box product in the initial notation is given as epsilon ijk ui vj wk. You don't need to remember this can be shown very quickly, but for now I'll take it as a known. Now we can see that the things are getting somewhere, because on the left hand side or in expression A we have the mod form with the three vectors, and the right hand side or in expression B we have the initial way. So this is the expression we have to show. So I'll put it in brackets because we haven't shown it yet. So in expression A we have three vectors as the three rows. In place of these three vectors, we can also substitute three rows of A. So I can basically assume that the vector u comprises the first row of A. So the first row of A has three numbers, which are three components forming the vector u. And similarly, vector v is the second row of A. And w is the third row of A. Now if we do this and we use A and B, so let's call this C. So if we use C in A and B, So the right hand side of A becomes, and the right hand side of B becomes, so where we had ui, that becomes an a1i. So you replace I with 1, you get a11, I with 2, you get a12, and I with 3, you get a13. So you get the three components of the first row of A. Similarly, you get the other two vectors as well. And this is exactly what we had to show. So we have successfully shown that the determinant of A is actually equal to the expression epsilon ijk a1i a2j a3k. So that completes the solution. So in problem 3, we have to show that this determinant is equal to epsilon mnp epsilon qrs determinant of A. Now A is a matrix and its determinant is simply given as this. Now the idea we want to use here is that if I swap the first and the second columns of A, let us see what happens. Now we know and we have shown that if we swap any two columns or rows, the sign of the determinant changes. So this becomes actually equal to minus determinant of A. So can I write this as epsilon 2, 1, 3? And the one above is written as, let's use determinant to the right hand side, epsilon 1, 2, 3 times determinant of A, where the first, second, and the third indices are simply the column numbers 1, 2, and 3. So if we swap the first two columns, the indices are, let's use a different color, 2, 1, and 3. So we have 2, 1, and 3, right? So this is a known relationship, so we have used that. But we are seeing a pattern here. I can, in fact, replace this 2, 1, and 3, or 1, 2, and 3, whatever you want to call it, with arbitrary indices. In this case, we'll call them Q, R, and S. So let's do that. So we'll write A1Q, A1R, and A1S, and so on. So this is equal to epsilon QRS times determinant of A. Let's check it out. So if I substitute 1, 2, and 3 in QRS, we simply get determinant of A. If I use the values 2, 1, and 3, that's a swap of first and second column as we showed here. So that's equal to epsilon 2, 1, 3, that's minus 1 times determinant of A. Every swap results in the change of the sign because of this epsilon that we have here. So we have shown this through a pattern. Now similarly, we can also apply this idea to row swaps. Let's see how. So if I swap the first and the second rows here, the sign will again change. So the same idea brings in another epsilon. So we'll simply write this as so now we have the first index becoming either an M or an N or a P. On the right hand side, we'll have an epsilon MNP times epsilon QRS times determinant of A. So this is quite general in the sense that this allows for any column or row swap and helps us determine the sign of the determinant. Remember, these values are simply either a 1 or a minus 1. Of course, you won't have the indices becoming the same, because if any two indices in a given epsilon become the same, epsilon becomes 0, and so does the determinant, because then resulting in a singular matrix. So this is exactly what we had to show. So this completes the solution. Now again, this relationship that we have shown, or that we were expected to show, is an important one. In fact, this is used as a starting point to prove the epsilon delta identity. So I will leave it to you to figure out how to do that, but I'll provide a hint here that if you use a Kronecker delta in place of A, see what happens. So let us now move to the fourth problem from today's tutorial. So this problem is asking us to show that sigma ii, that is the scalar that is formed through a contraction on sigma ij, that is sigma ii, is an invariant. Now if you recall the definition of an invariant, that was that a scalar quantity that has been synthesized from a tensor is an invariant if its value does not change upon an arbitrary rotational, or more generally an orthogonal transformation of the coordinate axes. So let us show that. So I'll use the symbol 1 sigma for this, and let's call this sigma ii, which, just to show, is actually a sum of the three diagonal elements of sigma in the matrix representation. So that's a sigma 1 1 plus sigma 2 2 plus sigma 3 3. But that's immaterial right now. Let's proceed with the solution. Now when we rotate the coordinate system, let us say we get the primed coordinate system. So in that we get a sigma ij prime. So this quantity becomes sigma I prime, which we'll call I sigma prime. And what we have to show is that the invariant, or the quantity sigma I prime, is equal to I sigma. So let's start with the left hand side. So that's the I of sigma prime, that's a transformed. So let's write what sigma prime ij is first. That, you know, from the tensor transformation rule, is AIP AJQ times sigma PQ. So this is the forward transformation that allows us to go from a sigma to a sigma prime. Now what we'll do is we will substitute j equals I here. I'll do it in the same expression. So this becomes sigma I prime, and this becomes AIQ. Now we will try to use the orthogonal property of the transformation matrix. So we'll write this as A transpose PI AIQ, and this remains a sigma PQ. So we can see that this is nothing but A transpose times A, which becomes a delta PQ, and this is a sigma PQ. And when I apply the substitution property of delta, this becomes sigma PP, which can also be written as sigma II, because the indices P and I are dummy here. So what we have shown is that sigma prime II is sigma II, and again we did not assume any particular form for sigma. Sigma was arbitrary, and so was the orthogonal transformation, that is the matrix A. So we just use the property that A transpose A is identity, which is a property of an orthogonal matrix. There was nothing else assumed in this case. So this completes the proof that we have shown that the quantity sigma II is an invariant. In fact, this has a name. This is called the trace of the tensor or a matrix sigma, sometimes also written as TR of sigma. We will discuss more about it when we talk about invariance as a part of principal values and principal directions lecture next week. But The reason I wrote this as this 1 sigma is because this quantity is actually called the first invariant. It's a very important quantity of the tensor sigma ij. Again, for solving this problem, you don't need to know it's called the first invariant, but I'm just telling you that because through every problem, we learn something about quantities and continuum mechanics. So the next problem asks us that we have to find the transformation matrix A for a transformation which is a 45-degree clockwise rotation about the x3 axis. So let us draw this transformation first. So this is what the transformation looks like. Let's write the angles as well. So x3 prime coincides with x3, so there's nothing there. x2 prime rotates 45 degrees and so does x1. Sorry, this is x1 prime. So x1 prime or x1 also rotates by 45 degrees to get x1 prime. So let's write the transformation matrix now. Now remember the transformation matrix, if you write it as A11, the first index denotes the primed axis and the second index denotes the non-primed axis. So let's write the components. So the angle between x1 prime and x1 is 45 degrees. So this becomes cos of 45, that is 1 upon root 2. The angle between x1 prime and x2 is 90 plus 45. So that becomes a minus 1 by root 2. And then x1 prime and x3 is still a 90. So that's a 0. Similarly, now let's go to x2 prime. x2 prime makes an angle of 45 degrees with x1. So that's a 1 by root 2. x2 prime makes an angle of 45 again with x2. So that's a 1 by root 2 again. And it's still a 90 degree with x3. So that's a 0. Now x3 prime makes an angle of 90 degrees with both x1 and x2. And then it makes an angle of 0 degrees with x3. So that's a 1. So this is the transformation matrix corresponding to this transformation that was given to us. So that completes the solution. So let us look at problem number 6 now. The problem states that we have to show that Kronecker delta, that's delta ij, is the only second order isotropic tensor. We had mentioned this in the previous lectures, but today we will show that through a problem. Now the job here is to show that it is the only second order isotropic tensor. So as a part of the problem, the following approach is suggested. So we will start with an arbitrary second order tensor sigma ij, which has 9 components, and we'll assume it to be isotropic. So what that means is that under any orthogonal transformation, sigma will remain the same. That is, sigma prime is going to be sigma. Now, of course, we cannot apply all the infinite transformations. So we will, as a part of step number 2 is suggested, so we perform some smartly chosen transformations to go from sigma ij to delta ij ultimately. So the first transformation suggested is a 120-degree counterclockwise rotation about n hat, and the second one suggested is a 90-degree counterclockwise rotation about x3. So what will happen is that finally we will get sigma ij equals delta ij. And since we started with 9 independent components of sigma and applied just 2 transformations to get to delta, so that shows that delta is the only second order isotropic tensor. So let us start looking at the solution. Now since the solution is long, I have written the solution already. So please follow the cursor to understand the flow of the discussion. So we have a sigma with 9 independent components as we discussed. And first we apply the 120-degree counterclockwise rotation about n hat. Now the way to visualize the red or the primed coordinate axes is that since E1 plus E2 plus E3 is an axis of symmetry, So a total of 360 degrees rotation counterclockwise will result in the exact same axis. So this is something you will have to visualize. And if I rotate it 120 degrees, so I'll see that E1 hat or x1 will go to x2. Another 120 degrees and it goes to x3. Another 120 degrees, it comes back to the original location. So using this, we can find the transformation matrix A now. So since x1 prime coincides with x2, so this component is 1 because the first index, that is a row index in transformation matrix, denotes the primed axis. The second row, which is for x2 prime coincides with x3, so this is 1 here and we have a 1 here. So now with this transformation matrix A, we can find sigma prime. So sigma prime is A sigma A transpose. So we put in the A sigma and A transpose like this, and we then simply will multiply them. So the first thing we do is we multiply the A with sigma, which gives us this matrix. Now you can do it component by component, but I'll just tell you that this form of the matrix A that we have got, where the ones have just moved locations, is actually called a permutation matrix. So what we see is that left multiplication by a permutation matrix is simply reordering the rows of a matrix. So what we've seen is, if you look at the order, we have 1 appearing at the second location, so I'll write a 2 here. Then we have 1 appearing at the third location, so I'll write a 3 here. And then we have a 1 appearing at the first location. So the order is 2, 3, 1. So now what we see is that the second row of sigma comes first, then we have the third row, and then we have the first row. Again, you don't need to remember this, but permutation matrices are quite common in different domains in mathematics. So I'm just telling you that. All right, so let's move on further. Now we'll do the multiplication of sigma with this A transpose. Now A transpose is also a permutation matrix, and if we have a permutation matrix multiplication to the right, then it's column movement. So we notice that in the first column we have 1 appearing at the second location, in the second column we have 1 appearing at the third location, and in the third column we have 1 appearing at the first location. Right. So what we see is that we have the second column of sigma first, then we have the third column of sigma second, and then we have the first column of sigma third. So as I said, permutation matrix multiplied to the right is column movement. So this is what we have, and we get the final sigma prime. So this is sigma prime. Now we know that sigma prime is equal to sigma because it's an isotropic tensor. That's what we have assumed. So we write the sigma here. So this is equal to sigma. So we equate component by component, because if you have two second order tensors equal to each other, then that means their corresponding components are the same. So when you do that, so first you see that sigma 1 1 equal to sigma 2 2 equal to sigma 3 3. So all the diagonal components are the same, and you get this conditions as well, which ultimately transforms to these two conditions. So what this means is that we can represent sigma using just three constants now, A, B, and C. So this is the simplified form of sigma after applying first. The first transform. Now we apply the second transform. to further simplify this and get rid of B and C. So the second transform we apply is 90-degree counterclockwise rotation about x3. Now that's something we already have discussed, so I'll quickly go through. So we have the matrix A looking like this. You find sigma prime as A sigma A transpose. That gives you this as sigma prime. And as we know that sigma prime is equal to sigma, so we write the sigma just the same as what we had here, and they are equal. So when you equate component by component, we don't have to do much. We simply see that B equals minus C and B equals C. So that means C is 0 and so is B. So finally, our sigma has this form where it is a scalar times delta Ij. So what we have seen is that a scalar times delta Ij is the only second order isotropic tensor. So this completes the problem solution. I hope you enjoyed this problem. And as I said, this is slightly longer, so I did not solve it in the class today, but I expect you to please practice it. So today we solved 6 problems from the topics on matrices and determinants, tensor transformations, and isotropy and invariance. So thank you very much, and I'll see you next week with a discussion on principal values, principal directions, and tensor calculus. Thank you.